Professor Shea holds his PhD in physics from Harvard. Back in '97, he did a postdoctoral fellowship at IBM Research, and then spent a number of years at Bell Labs, which was then part of Lucent Technologies, where he studied the reliability of MEMS, microelectromechanical systems. But since 2004, he has been on the faculty at EPFL, and his research there centers on electrically driven elastomer-based actuators for things like wearables and haptics and soft robotics. So he's joining us here today to talk about soft machines hard at work, and should note that he's joining from Switzerland via the wonders of Zoom, and so it's late on a Friday night, and he's been extraordinarily gracious with his time. And let's give Professor Shea a warm welcome. And by the way, I should say, if anyone wants to ask a question during the talk, raise your hand, get my attention. We'll run a microphone up to you, and then of course we'll have some time for Q&A at the end as well. Okay, let's give him a warm welcome. Thank you.
Ed, thank you very much. It's really a pleasure to be able to talk with you here. I do wish I were there in person, but we'll sort that out some other time. So Ed is as well. So Ed, well, you have many fascinating people at Northwestern, so you're jealous of your faculty. Okay, so I'm going to talk about what my lab does on soft actuators. We are pretty much technology push. We work on actuators, and what we want to do is make actuators that are essentially soft enough that when you're on your body, you don't feel them, but yet somehow can give you some force. So we're going to be using electrostatic forces because I have a problem with pneumatics. I think it makes control very difficult. It makes untethered systems difficult. So we focus on electrically driven devices. And an example would be this thing in the middle here. It's an 18 micron thick dielectric elastomer actuator that is, you can put on your body, and then you can turn different pieces on, and that could make different objects sort of have some kind of augmented reality or augmented touch for things. Everything you're going to see in my slides are going to either be transparent because they're soft silicones, or they're going to be black because they're conductive carbon-based inks. So we're very bad at control. We tend to use control as on-off, and our justification for that is that soft things have different control means, and you don't want to have active control. So I'll just make a little side story on this little spin-off we have from my lab, which is using electroadhesion and very soft compliant fingers as a gripper. And so here the control is simple. It's on-off. You turn it on, it grips the banana. Turn it off, it lets go of the banana, and you have a little side-to-side motion. So I like this because we're using soft materials to do the shape adaptation. You could argue that the only shape we can get is the shape of the banana or the pear or whatever it is, but that tends to be the shape we want. So I'll use that as a example of why you might need less control with soft machines. But I want to focus today more on using these soft machines on our bodies for wearable haptics. I think that's a very good application of soft robotics. Instead of trying to replace some nice electromagnetic motor, use the soft machines where you really want the softness. And so I'll be also talking about some of these devices here. These are zipping electrostatic devices, and they allow you to get these large deformations, and I'll show at the very end how you can actually make them properly soft and making them entirely out of silicones. So I'd like to start by talking about the sense of touch a bit, and then get into 3 ways that in my lab we've been trying to make wearable haptic devices. Ed, you can still hear me? Everything's okay? I don't see any disaster. Okay.
Everything's great.
Right, so thank you, Ed. Thank you. The sense of touch is, well, something that we use every day without thinking about it very much. It's very intuitive, has a lot of emotional content, easy to decipher, but very much underused in virtual reality and augmented reality. So why is that? Is there a good reason for this? Well, we do have some kind of haptic feedback from the nice devices we play with, PlayStation controller or your watch or your phone. But basically, it's typically a buzzer or some very, very simple clicking type thing. It doesn't give you the sense of touch of touching fabric or of hugging that tree or of just sliding your fingers over a keyboard has so much rich information. And we know a lot of things in our life about, is your coffee cup sliding, what kind of clothes are you wearing, just by the sense of touch. And we don't have that. So we can go just do a little historical tour. What do we have in terms of haptics? If we look at VR, whoops, I'm missing the slide, I'm missing this one here. So the earliest thing I could find was in the 1960s. This was the Sensorama. And so this was the first immersive VR. So what did they have? Well, they had stereo vision, they had stereo sound, they could blow smells at you, they could blow air in your face, and they could tilt the seat. But you didn't have much by sense of touch. Is that because it was difficult? Is it difficult to make things that give you a sense of touch? What's going on? The next big step forward was Ivan Sutherland with his so-called Sword of Damocles. So he had this visionary paper where he imagined what we could think of, or maybe the older ones in this room can think of as the Star Trek holodeck. So I'll read his ultimate display. Ultimate display would, of course, be a room within which the computer can control the existence of matter. A chair displayed in such a room would be good enough to sit in. Handcuffs displayed in such a room would be confining, and a bullet displayed in such a room would kill. So he's imagining this VR world where you can really touch things to the point that the bullet kills you. So what I found so fascinating with him is that at the time when he was writing the paper, display technology was so horrible that he imagined that the progress in display technology and in haptics would be comparable. And of course, it turns out that that's not the case, that the progress in display technology is fantastic and progress in haptics is not. But let's have a quick look at what his video graphics were like in the 60s. So here he is, it's a head-mounted display, kind of like an Oculus Quest, but the 1960s version, that you black and white. But it does have room tracking, so it can actually track his gaze. And this is what he sees with the wonderful, beautiful 1960s graphics where you can make a cube. Looks a bit like the first Star Wars movie. Okay, so this is what he had, and that's why he couldn't imagine, why that we would get to the point of today where we have these fantastic displays and still pretty much just little vibrating piezoeccentric motors on a glove as your haptic feedback. Okay, so get your multiple million pixels per eyeball for a pretty reasonable cost. Pay a bit more if you want the industrial version. Why? Well, why is touch more difficult? So I have a trivial explanation. Computer's not very happy here. Try to get my trivial explanation. My trivial explanation is that the area of your eyes is a centimeter squared, and the area of your skin is multiple square meters. So you have this first practical problem that if you want haptics, as in sort of Ready Player One, all over your body, you're going to have to cover a couple of square meters with actuators, and that's not going to be easy. There's perhaps a better argument, which is that how much power do I need to see something? I probably need a few milliwatts of optical power beamed onto my retina, and I can see everything perfectly. But if I'm trying to make some immersive haptics, I might need several hundreds, maybe 1,000 watts of mechanical work done on the body to feel something. And so that's a big difference. There are many orders of magnitude difference between what I need to see and what I need to feel. And that's perhaps also why it's difficult to have a sense of touch. A third thing is that, do you really need a sense of touch? I mean, we're so visually dominated that you can get away with a lot of things just being visual. And that's going to help us for haptics later, because we can make horrible actuators that are still convincing as long as you have your VR headset on. All right, onwards. Why would you want to do all this? Is it for gaming? Is it for some more industrial application? We have a lot of interest from typically car manufacturers who want to develop manufacturable systems and be able to figure out ahead of time how you would route cables, teleoperation, AR, and then what do you wear? Is it just a VR headset? Is it a glove? Is it a whole suit? Is that socially acceptable? Is it a fashion symbol? I mean, is it a status symbol? What do you want? Depends very much on the application you're trying to get to, and how much effort are you going to put into putting that on. We make gloves. The gloves have to, you have to just slide them on. If as in early gloves, it takes half an hour to carefully dimension it and then wrap it around. If it takes half an hour to get your glove on, few people are going to be willing to do this. And then it's only going to be restricted to a very, very small set of individuals. How many degrees of freedom you want, that again depends on what you're trying to do. So a couple of examples. This one is from a car manufacturer. Here, there's kind of an obvious use case of saying, well, if I'm going to design a car to be repairable or manufacturable, I need to figure out how I'm going to put my pieces in there. And the best way to do that is by actually feeling it. Or if I want to train a new employee, well, the best way to train an employee is by having this VR headset with a sense of touch. And that's what's missing today, is that proper sense of touch. Here's a nice example where the sense of touch is completely missing, yet completely central. So here we have a scenario which would be some medical training. You're practicing, in this case, stapling closed this wound, but you can see the user has no haptic feedback other than some buzzing in her hand. So you can do something, but there's a lot of things, a lot is lacking. All right. So, oops, keep getting ahead of myself. Now, there are, of course, beautiful force feedback systems. The Da Vinci robot has these nice force feedback that are very accurate. These force feedbacks are really quite amazing in terms of how well they work. They're just very heavy. There's this MIT Media Lab, their tangible surface, which is amazing, and it's very fast. You get these large deformations. It reacts to touch. If you have a projector on top, you can make nice cool colors on it. It works great as a haptic surface, but it's not wearable. And what you'll see in a second after we zoom out from Sean is that you'll see how it basically takes a cubic meter of actuators to get this thing to work. So for your work surface, you have under it more than a cubic meter of support. So it's just not wearable. So let's see something wearable. So here, from our favorite company that lost 25% of its stock value today, here we have a very happy Oculus employee. And what is she doing? So she has on her head a VR headset. You can see the little balls that are used for the optical tracking. Her gloves have lots of these nice little markers. So there's a computer system somewhere that knows very accurately where her hand is, what her hand pose is, and how her body is posed. And what she has, to my understanding, is there's little basically piezo buzzers at the edge of her fingertip, so that when she touches something, she can feel a buzzing. And she's on the left, you see an external camera view of this user, and on the right, you see what's in her headset. So I have to admit, she does look like she's having an awfully good time with this. So she's playing Jenga, pushing these bricks around, and you can see she's grabbing them pretty accurately. She's able to, it's a pretty delicate task, and the system is very nicely rendered. So she can push things in position. She obviously gets pretty good feedback as to where the object is. She's holding the rubber ducky pretty well. Touch him, and then of course, what would you do? You'll toss him to the ground. So great. So I think this is actually a pretty good example of how visually dominated you can be, because she's actually only feeling buzzing in her fingers when she touches the wood blocks, and yet she's able to do a very good job. So I'm going to claim that what's missing here is this sense of touch properly. Can she tell if she's touching a duck, a sponge, a tennis ball, or a metal block? Probably not. And we would like to add that in there to make real objects feel, well, better, and then that makes for a more immersive experience. So if, as you probably all know, in haptics, you can divide things into two gross categories, kinesthetic and cutaneous. And I have examples here of a kinesthetic glove. So the kinesthetic is basically blocking or imposing motion on the joints. So not and cutaneous is a nice delicate sense of touch you get in your fingertips, well, all over your body, but mostly are using our fingertips for exploring the world. So the kinesthetic, you could imagine you have this Terminator-like looking thing that blocks your hands. That works quite nicely. And on the bottom, I have a really nice device I like very much from Okamura's lab. It's basically a delta robot on a fingertip. So you can put normal and shear forces from the 6 degree of freedom. Well, I guess it uses a 3 degree of freedom, little delta robot. Very, very, very clever. The problem with the things I have on the screen, it's not really wearable. And so what I'd like to say is, how can we make this wearable? I have to solve an energy problem. There's a control problem, but there's mostly just, I need to make the actuators really, really tiny and fit on the skin so I can make this wearable. And that's what I want to talk about. So how can we make this wearable? You're going to have to use different materials. You're going to have to use something soft, because if you use something hard, that's just not going to be a nice, convenient wearable device. So we're going to be talking about elastomers typically, and then we're going to need some means of deforming those elastomers. And I've already started whining that I don't like pneumatic systems, because it's okay if you have one actuator, but if you have a kind of a braille display and you have 1,000 independent pneumatic systems, even if you have a dozen pneumatic channels, life gets to be very hard, it gets to be slow. So I think all electrical control is very much the way to go for an integrated soft robot, especially on body. So I need a soft actuator. Okay, I need a soft actuator. And I'm going to be greedy. I want my soft actuator to have high strain. I want it to have high energy density, high power density. I want it to be fast. I want it to be reliable. I need all these things because I want things to be untethered, and I want them to be very thin form factor. So the table is kind of an overview, right? These tables are always very painful to make. And then everybody whines when you make a table because you forgot their work. But the biggest problem with these tables is that you typically can't have all the columns at once. So if I take a dielectric elastomer actuator, I cannot have the 1,000% strain and the 100 hertz operation and the strain rate of 10 to the 5% per second. You can't have them all at once. You only get one. And so that makes choosing things a bit more difficult. And then the most important column in this table is the one on the right, this auxiliary equipment. What does it take to actually run this? I mean, so if I'm, well, let's say I want to take a skeletal muscle, fine. Well, I need some kind of circulatory system. I need a respiratory system. The muscle doesn't just exist by itself. Same for a pneumatic actuator. Well, to get all these nice features, I need a pump. DEA, well, I'm going to need a kilovolt power supply. SMA, I'm going to need a high amperage power supply. So in terms of thinking what can be wearable, you also have to take into account what extra systems do I need to run things, and how tolerable is it going to be to have a big backpack to run a small little glove. So I'm going to focus on electrostatic devices because I'm going to claim that this is the most energy efficient way to go. I'll justify my claim in a bit, but for now, electrostatics, I like them because I don't have a compressor. I can go directly electrically, which makes control, integrating control and sensing and just autonomous systems much easier. They are fast, or they can be fast, get higher force density, high energy density. And what's bad? Well, what's bad is typically high voltages, in part because people don't like high voltages. I don't know why. People keep running away when I mention high voltages, but they're really not that dangerous. Actually, no, we make sure that they're not dangerous at all by limiting current. So high voltages, the problem with high voltages is the size of the power supply and the materials challenges that go with working at very high electric field. So, sorry, 2 equations, you'll survive. Let's imagine we have 2 electrodes in blue and a dielectric in green in between them, spaced by distance d. Dielectric has relative permittivity epsilon r, and the electrostatic force between my plates, even if you ignore which way things move, it just scales as relative permittivity times area times electric field squared. Now, if we look at energy density, things get even simpler. Energy density is just half of permittivity free space times relative permittivity times electric field squared. So I want to maximize my energy density. So to maximize my energy density, I'm going to want to maximize that product in red of relative permittivity times breakdown field. Okay, nice. What materials can I use? And are the soft materials I want to use in any way good for this? Well, you know the answer, it's no. So a lot of people, of course, have done this calculation before, and you can find tables where people look at breakdown field versus relative permittivity. Now, we would like to be up in the corner over here. Sadly, there's this empirical line plotting of breakdown voltage versus relative permittivity for which you are over here. So if you have a, say, silicon dioxide, aluminum oxide, piezo materials over here, PZT, barium strontium titanate are down here. And so there's this trade-off that if you go to higher relative permittivity, you lose in breakdown field. And note that, that this is the good line up here. If you're using elastomers, mylar, you're down here. If you're using polymers, you may be over there. So there's this limited set of materials we can use. I don't have a good physics argument for why there is this trade-off, but it is there. And so the dots in red are the ones we're going to be using. We're going to be using PDMS down here. And then there's this seemingly magic solution that's going to come and save us, this PVDF coater polymer that seems to be on that line along with all the ceramics. So we'll use that. And then we're going to have to deal with reality, which is that your dot moved from here to down here. But that's not so bad. Okay, so we want these materials high breakdown field. We want the high permittivity, and soft materials are just not going to be so good for this. And that's going to then raise the question of, well, do we have to use soft materials? I know I want something soft and wearable. How much of that has to be subject to electric field? Could I, rhetorical question, the answer is yes. Could I find some better architecture, perhaps using zipping, where I can use the high performance materials and still have parts that are soft in order to have my compliant system? Okay, so I'm going to talk about 3 different types of ways we use electrostatics for wearables. We're going to have sliding, that's just an electrostatic clutch. So we have different parts that slide here. We'll have a dielectric elastomer actuator that we're going to use for this imperceptible haptics. That's a very bad word, feel through haptics. And then finally, we'll have these zipping devices, which I think offer the most interesting performance. Okay, so let's start with this kinesthetic haptic issue. I'm wearing my VR goggles, life is good, I'm going to get coffee, and I need to avoid this. That's going to break my immersion. I don't want my hands to go to my coffee cup, virtual coffee cup. So how can I do that? Well, the way we've done it is using these electrostatic brakes. The idea is to go from something big like this nice Dexmo hand to something much lower format, where now the actuators that block the motion are less than 1 millimeter thick. And you can see that the glove, a lot of the work actually was not on the actuator. A lot of the work was on how do you get the actuators into the glove, and how do you get it to fit on your hand comfortably, and how do you do the grounding onto your wrist. That's where the challenges are, because the actuator, you'll see, is actually pretty easy. It's the integration after that's tricky. So what is this actuator that we put in there? It's just electrostatic clutch. So what you have is you have 2 electrodes here in gray with a dielectric in between. If the voltage is off, they can just slide. Turn the voltage on, the plates get pulled together, and now you have an electrostatic force that pulls them together, and you therefore have this frictional force down here that tells me how much I can block motion. And the nice thing about blocking motion from an energy perspective is that it costs you 0 energy. You're doing no work. So in principle, you could have a 0 energy solution. And this really works at milliwatts to block newtons, tens of newtons of force. So the little movie here shows how we're picking up a 2 kilo bag of apples. The key metrics over here that cost you roughly 1 milliwatt per square centimeter to block 20 newtons per square centimeter. So what does this look like? Whoops. This is a textile version. So we have essentially conductive textile coated with this high permittivity PVDF coater polymer. Ronan was touching the pieces together to show that it's not sticky. If you turn the 300 volt power supply on, however, these pieces get stuck together, and you get this, to me, unintuitively large force. Like that square centimeter picks up to 2 kilos. So then the guys went to the sports shop and bought a 20 kilo weight, and they could hold that with a 10 square centimeter clutch. So you can really get a lot of stuff done with very low energy consumption if you can integrate it into a format, into a textile format. The next challenge was say, okay, on-off is nice, but well, I want to know if I'm picking up a virtual brick or a virtual sponge. How am I going to do that? Well, I'm basically going to have to tune my voltage to allow controlled sliding. And so here you get into another haptic issue that all humans are different. And so you have to sort of go human by human and try and get things done. So this is how we do a typical collaboration. We have different objects here that we want to replicate the stiffness. And here, PhD student is holding a sponge, and in this hand he has the glove on, and we iterate down to, which was stiffer, the glove, stiffer the sponge, and that gives us, okay, 47 volts for him is the voltage that corresponds to a sponge. 78 corresponds to a bottle, and cotton wool is 22. And in that way, you can start to build up this library that's individualized to each user for what voltage you need to do it. So this is here is an average over 13 people, but if you're going to make something realistic, you don't want to use the average, you want to use the right value for each person, which is not so great if you're trying to sell these. Okay, so how does, what scenario do we, what VR test did we do? We essentially made these 5 cubes and allowed the user to put his or her finger inside the cube, wiggle the finger around, and sort the cubes from softest to hardest. And they do that quite nicely. I think these videos are always, to me, very amusing. So on the right, you have the VR mounted camera view of the world. And on the left, you have what the user is seeing. And here the user is then exploring the different cubes and sorts them from softest to hardest. So that works pretty well. Yeah. But could you, that's nice for the hand, okay. What about more of the body? How can you make something thin and wearable for the whole body? How do you deal with grounding? I mean, if you want to transmit large forces, you have to transmit them somewhere. You have to transmit them to the ground or the wall. And the typical problem in VR is, how do I give an object weight? Like, everything has no weight. It's not so problematic because we're visually dominated, but it is kind of annoying that you'd like to have things weigh something without having to go for this nice DLR KUKA collaboration where you get tied to big robotic arms. And it turns out that we took the same clutch we had on the fingers and just made a bigger version and put it on the elbow. Said, okay, now imagine you're picking up an object by bending your elbows. Can you not feel weight, but you can feel inertia? So, and this worked, I must say, pretty nicely. So essentially here we have our happy user. He has a 1 kilo weight dangling from his wrist. And here he's going to move his arm. And that allows him to remember what it feels like to lift 1 kilo this way. And then we're going to lift the weight and turn on the clutch and say, okay, now what voltage do we need to make that resistance of your elbow feel the same as a 1 kilo weight? And that, though it's not weight, it's inertia, it worked quite well in allowing users to then pick up these cubes and tell which cube weighed more than the other by constraining the elbow, and then in another study constraining the shoulder, which is a lot more difficult because you have many more degrees of freedom to constrain on the shoulder. So I think that these clutches are an interesting way to in a very low energy manner, control kinesthetic haptics. All right. Next, I'm going to go on to more cutaneous haptics and start with the DEA because it worked way better than I ever thought it would, and then go to zipping because I think that's a more promising solution. So dielectric elastomer actuators are these soft actuators where you have an elastomer in blue, compliant electrodes, so stretchable electrodes that has to be softer than the elastomer in gray. Put a high voltage between them, and you get Maxwell pressure and compress your elastomer, and you get potentially large strains. More realistically, if you want to do something easy with silicones, maybe 20% strain. But and the voltages typically used are 1 to 5 kilovolts, not because we love high voltages, we don't, but because we want to work close to the breakdown field of the material to get the large strain. And if you use, say, a 10 or 20 micron film, you're talking about 2 to 5 kilovolts operating. So we tried to solve that. And what's the motivation? Well, the motivation is field through haptics. So here you see, again, this nice Delta robot on a fingertip from Fédérale. And it doesn't allow you to do anything with your finger. You can't actually pick up an object because you have this Delta robot on your finger. So there's been some really nice work from Strangler's group at the University of Sutherland using what they call tattoos for field through haptics. So the idea is that you have this temporary tattoo-like object that stimulates your mechanoreceptors in your finger directly, basically electrocutes you. So it drives current through your finger. And the idea is that instead of stimulating your mechanoreceptors by touching an object, you stimulate the mechanoreceptors by electricity. It works, and so the whole device is very thin. It works pretty nicely. It feels really weird. I tried these once because essentially you feel like you're being electrocuted. And you pull your hand back to try and get away from it, but it's stuck to your finger. So you can do all of the pulling back of your hand you want to, you're still stuck on your finger. But I thought the concept was great to have something that's so thin that you can't feel it. And then you depending on what you turn it on, your objects have a different sense of touch, and you can control that actively. And you don't have to sense just touch. You could be feeling anything. You could be feeling light color. You could be feeling proximity. You could be feeling anything you want to could become a sense of touch on your finger. So we thought this was really exciting, and we wanted to do it mechanically because the electrostimulation is not so great. And so to do that, we had to have a very, very thin dielectric elastomer actuator, and we wanted to have low voltage for a reason I'll explain to later related to power supply size. So I don't have time to go through the technology, how we did this. We ended up with a 6 micron thick dielectric elastomer and stacked 3 of them high to get more force. By playing with electrodes, essentially aligning carbon nanotubes in a Langmuir-Scheffer process, we ended up with DAs that worked below 500 volts and at 500 hertz. Okay, so now you can put this on your finger. Here we go. Here's your dielectric elastomer actuator in the middle, and it's 18 microns thick, so it's thin enough that you don't really feel it. And then the miracle is, well, does it actually give you anything that you can feel if you turn it on? And so here is actually a not very high magnification, low magnification microscope image of fingertips and fingerprints. So you can see the fingerprints, the fingerprint ridges. And as you're turning the DEA on and off, it stretches them. And to my surprise, this actually works really nicely. You can really feel this. You feel this at 1 hertz, you feel it tapping exactly where the DEA is. At 5 hertz, you also feel it tapping exactly where the DEA is. And then as you go up in frequency, you start to feel a buzzing that's more diffuse because, well, that's how our mechanoreceptors work, that we're not able to very accurately determine where buzzing is. And that's why people use buzzing things for haptic feedback, because it doesn't really matter where you mount it, you still feel it roughly in that region. So here we're happy. Off, you can't really feel it. On, you can feel it. Now the 500 volt issue. So the voltages for me are really not a safety issue because we know how to work with that. It's a bulk of the power supply. I'm not talking about 10 kilo power supplies, but still, if you're making a multi-kilovolt power supply, it's going to cost you a few grams. And for a wearable device, especially a multi-channel wearable device, that's not really tolerable. So this is our 1-channel 5 kilovolt supply, weighs 15 grams. Works great, but it's still 15 grams. It turns out that below 500 volts, maybe 600 or 700 volts, you can get standard SMD components that allow you to make a much, much lower mass power supply. So here is a 2-channel 500 volt, but 1 kilohertz, not 1 hertz, 1 kilohertz power supply at 350 milligrams. So we use that for a little mobile robot, and then we use the simpler version of that for our haptics. So how do we do that? Whoops, what's going on over here? Screen looks a little bit weird. So here, wonderful finger. And on the back of the fingernail, we mounted these little electronics. You can see most of it is actually the lithium polymer battery. The DEA is over here on the front. And these 2 things that look like eyes are basically eyes. They're photodiodes. And the way this thing is programmed is that if the photodiodes see white paper, they do nothing. The device is off. If the photodiodes see black ink, then they're going to turn the DEA on at 100 hertz so that you can feel it. And so now the cool thing is you can now see with your finger. And in this case, we can see the color of ink, but you could have this differentiate different colors or do different things. So the demo over here is Xiaobing and Jingjiang. And so Jingjiang randomizes the EPFL letters, covers them with a smooth sheet of plastic, and Xiaobing, he's now exploring this and he feels
this is P.
That's letter P. And then he keeps on going and he finds letter F.
This is
just
F.
using a sense of not touch, touch, but he's going on a flat plastic piece. Okay, I grant
This
you
is
there are
E.
4 letters in EPFL. That last L is pretty hard to get wrong.
This is L.
It is a little bit more amusing when Jing Chang organizes letters differently and rotates them. So here is a much harder task. You'll see it takes Xiaobing a lot longer to figure out which letter is which. And when I saw this live the first time, it was very funny because Xiaobing didn't know that Jing Chang had rotated the letters, and he was going nuts trying to figure out what was going on. And you could just see the lamp bulb go on over his head when he figured out what they were doing. All right,
This is the P.
so you can use your fingers to see letters. But to give you the full story, these DA devices have a very short lifetime. Like they'll work for 2-3 hours, but you can't really pull them off and put them on another user. It's a bit annoying when it takes you so long to make them. And so is there a way to get some of the benefits of these soft devices with a much higher energy density and with a much more robust material set? Rhetorical questions, the answer is always yes. It would be to use some kind of zipping devices. So the zipping devices, because you're working in a much better region of that breakdown voltage versus permittivity plot, they can give you much higher energy density than the DAs, which were kind of in the lower left corner because of the silicones. So the way it works is you have 2 conductors here in gray, a dielectric in green in between, put a voltage between them, and your device is zipped down. This has been known for many decades and used in MEMS, and quite a few groups are now using it in soft robotics. It has also a nice advantage that the electrodes can just be normal metallization. You can just have metallized mylar. That's your electrode. Don't need any fancy stretchable electrodes. Makes life much easier. So many groups are doing this. Actually, today I just saw a very cool paper from Tim Helps in Roster's group in Science Robotics using these zipping technologies. So I'll just and the other very well-known group doing zipping is Christopher Keplinger now at the Max Planck Institute in Germany. But I'll just give a little movie from an electro ribbon zipping actuator from Jonathan's group. Hopefully this works. So here they have essentially just 2 conductors and they put a voltage between them, and then you get this large zipping. The secret sauce they use is the droplet of oil. There's a little droplet of oil right in the corner, and that's what they need to prevent the breakdown. Very clever, and this works nicely, but you can see these large strains that you can get because you're using the zipping. You have a force versus strain trade-off, force versus displacement trade-off as always, but you can get these large displacements. And so the way we did zipping was a little bit different. We added hydraulic coupling to it. So what we wanted was to have a zipping region on the sides. So you can see the zipping happening on the sides. This is in the green stuff is of course a high permittivity dielectric. And in the middle, we have this oil that gets pushed in, and the cavity is closed by a silicone membrane. And the nice thing here is that the silicone membrane can be very soft. The silicone membrane has no electric field applied across it. So from a silicone membrane, I don't have to care about permittivity or about breakdown field. And I can tune the thickness of my silicone and the diameter of this thing to get better performance and sort of trade off force versus displacement. And I get very high energy density because in here, I can use very good materials that don't have to be soft. They just have to bend. And bending is easy. Well, you have John Rogers has been doing this now for decades of showing how you can take very hard materials, make them thin, and you can sort of bend them to your will. So what this looks like in the first generation was like this. From the top, you could see the zipping, but from the side, you get this large strain. And because you have the high energy density, you actually have pretty good blocked forces. So in this case, 300 millinewtons for a small device. For haptics, for sense of touch, that's more than sufficient. They scale nicely. You can make them in different sizes. And again, this made for a very nice button. By being soft silicone, it's actually quite comfortable to touch. So you can poke at this thing, and they're actually very robust. You can squeeze them. They survive really quite nicely. So waiting for the guy our kind user to squeeze them. And yeah, so that works pretty well. And then what can you do? Well, when you touch something, you of course do feel a normal force. So if I'm holding my coffee cup, I do feel this normal force, but I also feel a shear force, right? I know how heavy this cup is, in part from kinesthetics, but also because I feel the shear force on mechanoreceptors in my finger. if you slide your hand across a keyboard or across any textile, you're feeling a lot of shear forces. So we want to be able to reproduce some of these shear forces too with our actuators. And that turns out to be pretty easy to do in this configuration by simply splitting the electrodes. So if, instead of having one electrode on the top, one at the bottom, well, you can have certainly make a kind of a cross thing, two at the bottom, two at the top, and then you can actuate each quadrant and now have a bump that moves not just up and down, but also side to side. And that was nice to do because you could then give much more interesting patterns to the users. You could tell it rotating one way, rotating another way, shifting sideways, just going up and down. There was a richer set of symbols you could start to display. And we did some user testing on this, or put it on a fingertip, and the users were pretty good at telling what was going on. Yeah, fine. You can, play with this in different ways that you want to. One fun way was to put it on the back of a watch, and then now on your wrist, you're feeling these different symbols. So you have notification that can be rotation, side to side motion, not just having your watch buzz, but have some richer set of information sent to your watch. You can also make some kind of crawling robots with these things, because now we have 6 of these. And if you synchronize them and you have basically a step up type of motion, you can have these things move. But I want to get back to wearables, because the wearables is what I find a lot more interesting. So this is still unpublished work, where now we improved the fabrication a lot and start to make arrays of them and control the array. And then you started exploring, well, okay, well, if I put it on the back of my hand, or the palm, or forearm, shoulder, back of the neck, lower back, all these places that have different 2-point discrimination thresholds, that have different sensitivities, that may be more or less hairy. And so having fun here, trying to explore how best you convey interesting haptic information this way. There's quite a few groups, well, for instance, John Rogers, who have these large arrays of haptics over the body. And it's really interesting to try and figure out, do we want it stuck on the skin? That's the nicest way to transmit the information. But is that what users want? Do they really want it stuck on their skin? Should it be a suit? How do we use this in a convincing manner, and a pleasing manner, and a socially acceptable manner? Last little movie, and then I wrap up, is a fully printed, stretchable, all silicone version of these devices. So, all right, so it's here. So this is an array. So it's all inkjet printed. Sorry for the fancy movie, but you can see 4 of these HAXELs over here. They're spaced by roughly 1 centimeter. You can turn them on one at a time. And the nice thing about having this in the soft silicone is that you can really wear it on your finger. And well, this actually works. I was surprised how well this worked. You can really distinguish each pixel. You can, Taxel, you can run them at different frequencies. You can do a lot of interesting things when you have this now stretchable that you can just wrap on around your finger. So I find this an exciting direction to go forward. I'll wrap up here. Hopefully I've told you about some interesting electrostatics, and maybe even convinced you that electrostatics and soft electrodes allow you to make very thin, high energy density, efficient wearable actuators. I really think that all electrical control is a very important way to go forward if you have a complex system. Not if you have one actuator, but if you have a complex system and you want to be portable, electrical control is a good way to go. There are many, many things that we haven't solved. There's a lot of integration issues. How do you add sensors in here? How do we control it? I mean, how do you close that feedback loop? What's the right system architecture? But it is an exciting field for us. We're thinking about, of course, wearable haptics. And a lot of the work now that we're doing is in making soft fibers. We have a lot of work coming up that we'll be happy to share soon on how you can make fiber-shaped actuators that are soft and you can weave. And that then really opens doors for a lot more wearables. I have the privilege of talking to you while other people really did the work. So I need to thank my team. I'd like to thank also some key collaborators. And I thank you very much for your attention. And I'm happy to take your questions.
All right, thank you. That was just terrific. And we have time for questions. So I will shuttle this around. raise your hand if you've got a question for Professor Shea. All right, we got one coming up here.
Hi. Really interested in the last bit you talked about, the what were they called? HAXELs?
We call them
HAXELs. Yeah.
HAXELs. They're very similar to the HAXEL devices from Christoph Keplinger's group.
Yeah. You know, the crawling robot is I think really the coolest thing, at least from my perspective. I know it's not entirely the target of your work, but I was just wondering, what is the scalability of this in terms of, you know, not only mass manufacturability, but also, you know, can this be made big, small? You know, would this work on the millimeter scale, for instance?
So it can be made small. I don't think it's a good idea to make it big. So we're actually making them in a clean room on 120 micron size. So I think it's really exciting to make them small, because then you could have an array of actuators very densely packed. You have to solve a bunch of addressing issues, but they scale down beautifully if you master the fabrication. You can scale them up. We've gone to a few centimeters, but then I think that's not the right. Then you're better off using really the HAXELs from Keplinger's group, because having the silicones and the elastomers in here is probably not so suited to larger devices. And you also have timescale issues and current issues. Like now you have to charge up these large capacitors. Yeah, you can, of course, but I'm not sure that. I think there's a certain size scale where these electrostatic actuators make sense. And then if you get bigger than that, probably other actuators are a better solution. It's a bit of a hand-wavy answer, sorry.
Oh, it was a great answer. If I could ask a quick follow-up on that, you said, if I understood, that you're getting scales down to 120 microns. I assume that's like a diameter of the axle itself.
Well, it's of the outer size. So the inner part is 50 microns, and then the pitch is 120.
Oh wow. Okay.
Yeah, there's a poor postdoc who was spending his life in the clean room.
What are the thicknesses of the layers then?
So that's where everything gets critical. So it's roughly 1 micron thickness for the elastomer, and well, that's the only then yeah. What else matters? It's sort of 10 microns or so for the polymers.
Wow, that's amazing. So do you maintain some of those robustness benefits when you get so small?
Yeah, so very fair question, and especially if you make an array of them, you have to have a high yield. But that's sort of work in progress. I find it very exciting because it will allow us to do reconfigurable microfluidics, where you use these little HAXELs to open and close channels, and you can do it very quickly. And if you do optical addressing, you can then reconfigure it very quickly. But it'll be a while before we can publish this with enough robustness.
That's super exciting. Super exciting. Those link scales. Other questions that we have? Oh, looks like we have something online.
Yeah.
Oh,
I have a question. Very interesting talk. And I guess what I'm quite curious about is you talked about like this disparity between the advance of graphics technology early on in your talk, and it's as you point out because of processing specializations of the brain. But I guess there's another gap in that people working on visual recognition algorithms, machine learning on vision have at their disposal a massive database of psychophysics and tasks such as identify this object in clutter, which they can test their algorithms against. And I guess I'm wondering, with respect to, for example, your cutaneous versus kinesthetic domains of haptic sense, is there any understanding with respect to, I guess, any task, picking up a cup or what have you, of I guess the natural signal statistics and that you can bang your work against and sort of say, here's where we need to tune things?
That's a very interesting question. Thank you. Which means I don't have an answer. Yes, surely there's. I think people call them haptic illusions, in as much as it's the understanding is so trivial that we're not even at the level of talking about psychophysics of touch. In a short-term practical point, we would love to exploit those to minimize how the fidelity of our actuators. But you're asking a more fundamental question, and I think there's a lot of work to be done to be able to answer that.
Okay. Yeah, thanks.
It would be fantastic to know how basically how our body works, and how also deal with just the different differences in perception between different people. I mean, like MP3 compression or all the video compression that we're using back and forth here, they work on all of us. And some of them have been trained or tuned to work on all of us. Just looking in my lab, basically very, very similar people have very different responses to touch.
It's a lot of variability in the population to deal with. Yeah.
That's a very good point, when we run into a lot in our work as well. Other questions? We still have a couple minutes here. Yep.
Thank you. That was a fascinating talk. For these haxels that you were showing us at the end here, what is the, I don't know, maximum actuation frequency if you're going to fully inflate or fully zip and unzip? What kinds of frequencies are you capable of?
Roughly 100 hertz. It depends on the size. So the bigger ones, like these, the big one over here, that's maybe 20 hertz. And these here are actually 2.5 centimeters across. They're monsters by our standards. They're also about 10 hertz. And then the smaller ones, like here, they'll work happily up to 100 hertz. It's then also a question of the power supply you use to divide it, because you're charging and discharging the capacitor pretty quickly, and we limit the current for safety, basically just that we don't want to have anybody have any issues. And then that's what limits really how fast we can drive the small ones on a wearable configuration.
And do you have a sense of what frequencies beyond which it wouldn't matter if you could drive higher than?
I would venture, well, so there's there's this interesting, well-known response versus frequency that in DC you need a lot more force than at 200 or 300 hertz where we're very exquisitely sensitive. So I would say beyond 400 or 500 hertz, there's no point trying to mechanically stimulate the skin anymore. So our problem is more that the displacement you need at 1 hertz is way higher by an order of magnitude or more than what you need at 200 hertz. That's also why people love to work with vibrations, because we can sense a micron of vibration. So we're more worried about getting displacement at the low end than displacement at the higher frequencies.
Thank you.
Okay, are there any other questions? Not seeing any. I think we should thank Professor Shea for a great talk. There you go.
Thank you very much. Thank you for your questions, and I'll hope to see you all in person sometime.